So far, we've been mostly talking about channel opening. So we've been talking about making an IV curve, which is measuring aspects of channel opening, and we've been talking about measuring conductance, which mostly people do when thinking about channel opening. But there are other things channels can do. So in this video, we're going to explore those other things, those other states channels can be in. And in particular, we're going to talk about a state called inactivation. And we're going to talk about how to, like, what it is, what it means, and then also how to measure how well activation is going for a particular channel. All right, let's go ahead and dive in. All right, so we are going to define inactivation, and we're going to talk about two ways of measuring inactivation, in particular, something called the pre-pulse technique, and then also graphs produced by the pre-pulse technique. Talk about what those look like, because we'll be seeing a lot of those in the rest of the course. So I want you to take a look at what is going on with this channel, both on a microscopic level and a macroscopic level. Right up here is what the voltage is doing. So this is a voltage clamp experiment. And at time zero, we're turning on the voltage and we're just going to hold it for 40 milliseconds and then we're going to turn it off. And for both of these, right, we're going to look what the channel is doing. So it looks here, it takes maybe a while for the channel to open up, but once it opens, it stays open more or less for the whole 40 milliseconds. And same here if you look at the macroscopic current. As long as that voltage is high, there is current going, there's the full current going. And so this is the voltage-gated potassium channel that's used in the action potential. It behaves like this. As long as the voltage is held high, the channels stay open. And so you can summarize the states of the channel like this. There's a closed state where there's no current, and there's an open state where there is current. And the way that you go between those is through depolarization, it goes from closed to open, or hyperpolarization, it goes from open to closed. For the most part, this is what is going to happen for outwardly rectifying channels. And an example of this, again, is the voltage-gated K plus channel used in the action potential. It's just very simple. When there's a high membrane potential, when there's that high voltage there, it will open and it will just stay open as long as that voltage is there. And when the voltage goes away, it goes back to being closed. Open, closed, simple. Now I would like you to look at this example, which is a little bit different. So in this one, we're also triggering a higher voltage at time zero, and we're holding it for 15 seconds. But I want you to look at what the channels are doing. So on an individual, on a microscopic level, each of these channels is opening, but they don't stay open. And it's not like the usual like randomness either. Like they're opening and closing and then opening again. No, they open for a bit and then they shut and they don't seem to pass current anymore. Okay, so this is very much unlike what was going on here, where as long as the voltage was high, the channel would be responding. Here, it seems like it responds for a bit, for a while, and then just doesn't. And you can see that in the macroscopic current as well. There's a lot of current initially, and then it just kind of goes away, even though the voltage is still high. Okay. And that's the important thing here. Even though, so out here, even though the membrane potential is still high, the current falls to close to zero. Okay. And an example of a channel that does this is the voltage-gated sodium channel, the one that's used in the action potential. And so this is a very important channel indeed, because this channel sets a lot of the properties of the action potential. So it's really important to understand how it behaves because this channel's properties help are the foundation, part of the foundation for how the action potential works, and how the action potential works is part of the foundation for epilepsy and other diseases like that. Okay, let's talk about that more. There's some sort of state that these channels can get into, where even when the activating stimulus is present, they can't pass current or they aren't passing current. So it's not simple as just open and closed. There is some sort of opening, but even though the stimulus is still there, it stops responding. When these are voltage dependent channels and this happens, we call this state the state of inactivation. We call the channels inactivated. And then this can also actually happen with ligand gated channels. Like if the ligand is still there and they stop responding, that is called desensitization. So that will come up later on in the course. For now, we're going to focus on inactivation because for now, we're going to focus on voltage gated channels. Okay. So for an inactivating voltage gated channels, we actually have three different states, not just two. We have our, we're not going to call it closed anymore because now there are two states that don't pass current. We're going to call it the resting state. And this is really from the resting membrane potential, although not all inactivating channels are at rest at the resting membrane potential. But yeah, whatever the state is where there's no current and there's low membrane potential, we're going to call that the resting state. And then when there and then when there's high voltage, it goes into the open state where it does pass current. But there's an extra state that there wasn't there before. So the open actually it goes to this inactivated state. And in this inactivated state, there's no current, but there's still the high membrane potential. And then finally, from the inactivated state, it goes into the resting state. So this is a super, super important diagram. Okay. And one of the most important things about it is just that there are these three different states that the channel can be in. And the other thing is the direction of the arrows. Nearly all of the time, it goes like this. It goes from resting to open to inactivated back to resting. That means you can't go, for the most part, you can't go straight from open back to resting again. You have to go through this inactivated state. It also means that you can't go, this is very important, you can't directly go from the inactivated state backwards to the open state. It has to go through this resting state first. Okay, so how do you go from state to state? Well, resting to open, we've talked about that kind of quite a lot. That has to do with depolarization. Depolarization triggers opening. How do you go from open to inactivated? That is also, it's going to take some time, and then it also takes just depolarization. The voltage has to be high. Okay, the voltage has to be, the membrane potential has to be in a depolarized state. That's going to cause an open channel to be inactivated. Okay, well, say a channel isn't activated, how do you get it to go back to being open? Well, it has to go through the resting state first. So how do you go from inactivated to resting? You need hyperpolarization. It takes time, doesn't happen immediately, and it takes hyperpolarization. So you have to return the resting, or sorry, you have to return the membrane potential back to a lower membrane potential to get back to your resting state, and then you can open again. So if the membrane potential is high, first you'll be in the open state, then you'll be in the inactivated state. But before the channel can open again, you got to bring it back to that lower kind of resting membrane potential in order to return the channel to rest before it can open again. So basically, in this video and the next video, we're going to talk about kind of different ways to measure for a given channel how well it goes from one state to another. We've already talked about how well it goes, how to measure how well it goes from the resting to the open. So we're going to talk about the other two. We're going to talk about how to measure how well it goes from the open to the inactivated state in this video. And in the next video, we're going to talk about how to measure how well it goes from the inactivated to the resting state. Okay, so just to clarify, how is being inactivated different from being in the resting state? So when a channel is resting, it's because the voltage is not at the right level to open the channel. It's too low. Um, so it's going to be here in the resting state. Here it's going to be open, and then along here, after some period of time, it's going to be in the inactivated state. And then you but the trick is here when the channel is inactivated, the voltage is at the right level. The voltage is high, but the channel is not passing current for some other reason. And when we talk about the biochemistry of the channels, we'll talk about exactly what's going on here to physically block the current from flowing, even though the membrane potential is high. And then here going back to this resting state there. Okay. So, this so if we're looking at this trace here, right, we just saw kind of it from the channel point of view. I want to talk about it from the current point of view. This is kind of a small version of that previous diagram here. Uh, when the membrane potential is low, the channels are going to be in this resting state. And then when you turn on your voltage clamp and clamp high, like at -10, that is going to cause the channels to open. You keep it at -10, you keep it high, you keep it high. The channels are going to slowly inactivate, and by the end here, a lot of them are inactivated. Um, and then how do you get them back to rest? Well, you have to turn off the voltage. You have to bring it down to a low voltage, and then the channels will go back into the resting state. So, talking more about that transition from open to inactivation. So what's going on here? You need the voltage to be high, and the higher the membrane potential, the more likely you are to get inactivation. It's kind of a stochastic thing, meaning a random thing per channel if you look here. So if you look at all these channels, they're not all inactivating at a certain time. Like these two channels inactivated very quickly, right? They opened and then they inactivated very soon. This one was open for far longer and then it only inactivated at this point. And so it's kind of like a probability kind of thing. Um, but there are things that influence that probability. The higher the membrane potential, the more likely you are to get inactivation. Also, time. When the channel is open for every period of time, there's a percentage chance it will inactivate. So the longer the channel is open, the more likely it is to enter inactivation. Okay, and so by the time you get here, you see nearly all of the channels are going to be in that inactivated state. So how do you measure how well inactivation is going to happen? And actually, why is this important? Well, it's because um, if the channels are not inactivated well, they might have problems going back into rest. Also, they might be passing too much current, and that could influence things like epilepsy. Okay, so how do we measure if there's a channel and there's a mutant channel, how well is that inactivation happening? Well, the simple way is to record the currents at time points where they should be inactivated. And the other is to conduct a pre-pulse experiment, and we'll talk about that. So let's talk about the simple thing first. So at time points long after the voltage stimulus begins, so like say we turn on the voltage here, and then right, that's gonna open the channels. And this is a voltage clamp experiment. And remember, the multiple lines means that we're testing a great many different voltages. This is actually like many experiments, not just one experiment. So when you turn it on, you record the currents and you analyze the peak current, and that's what you get for the IV curve. But if you wait a little while, like a bunch of them will start to inactivate, and you'll get currents all the way out. You'll get less current all the way out here. If you examine the currents all the way out here, that will tell you the raw amount of inactivation, right? It'll tell you at a point where all the channels are quote unquote supposed to be inactivated, how much current is or is not going through. So if you do it this way, the advantage is that it's pretty straightforward, pretty simple. You can measure this in the same experiment as when you're making IV curves. You just have to like keep your voltage on for a little longer and record the currents like after 10 milliseconds instead of right away at the peak. The disadvantage is that if you measure currents by this method, they're influenced by both the strength of inactivation and the strength of the initial currents. So if you want to figure out, so they're kind of all not the same. The idea is that like if you are doing it at -80, that's going to affect both like how much current you got initially, how many channels are open initially, and it's going to affect the amount of inactivation. So that's a little messy. And so another technique that gets around that issue is using the pre-pulse technique. So in this one, the voltage trace itself is a little more complicated. What you're going to do is you're going to pre-pulse, meaning you're going to hold the voltage at a given voltage for a long, long time. And then only at a certain point, you're going to have what's called a pulse. And this pulse is going to be something really high, like +20, that's like kind of guaranteed to open all of your channels if they're openable. Okay, so you're going to raise the voltage very high and see what happens. Um, so the idea here is that by having a very long pre-pulse, you're allowing whatever channels that will inactivate to inactivate at that stage. Um, and then during the pulse, you measure who can open, right? So if channels were inactivated over here, they wouldn't be able to open during the pulse, and that would decrease the current during the pulse. Okay, so what we do here eventually when we kind of graph the results, you will kind of graph this voltage. So along one end axis, the x-axis will be voltage, and then the y-axis will be current, but it won't be the current during the pre-pulse. It'll be the current during the pulse. Now you might be like, well, okay, if you pre-pulse at -90, well, at -90, all the channels should be in the resting state, right? That's really low. None of them should be open or inactivated, right? You're right. So the trick is you don't just pick one voltage to pre-pulse at, you actually pre-pulse at many different voltages. So again, the multiple lines means multiple experiments at different voltages. But so you pre-pulse at different voltages, you always pulse at the same voltage. And so that controls for the fact that different voltages will open different numbers of channels. You always pulse at +20 to like keep that the same. And again, what you graph on the x-axis, you'll be graphing all of these different voltages, and then at each voltage, you'll graph the currents during this time during the pulse. So here's what that will look like. And so now each current thing here is a different experiment where you had pulsed at a different pre-pulse. And then now what's being shown is the current during the actual pulse. And so what's going on here in the red? This is pre-pulsing at something like -90. At -90, there, as I mentioned before, all the channels should be in the resting state. They should not open. If they open, they have to open before they inactivate. And so there should be very little inactivation at -90. And so what that means is that when you pulse it to +20, they're all like, ah, and they all open up really big. And so you should get a high amplitude current during the pulse. You should get a lot of current during the pulse. And let's contrast that with pulsing at 0. So if you pulse at 0, which is actually a rather high voltage, that you pulse it, pulse it, pulse it. Most channels at some point during this pre-pulse period will open and then inactivate. The trick is the pre-pulse has to be a really long time, okay, a really long time, and to let all the channels that are going to inactivate. And as I mentioned, 0 is rather a high voltage, and so when you during the pulse, when you pulse it to 20, most of the channels will have been inactivated by then. They all like open and then inactivate, inactivate, inactivate. And so by the time you pulse it to 20, very, very few channels are left that can open, right? Because all these are stuck in the inactivated state. Remember to get out of the inactivated state, you have to go to rest. To go to rest, you need to lower the voltage again. You need to hyperpolarize, but we don't give them that chance. We give them straight from one high voltage, which is zero, to a super high voltage, which is 20. And so these channels are going to be stuck in the inactivated state. And so by the time you pulse them to 20, there aren't many channels left that can open. And so you're going to get a much lower amplitude of a current during the pulse because most of them will have been inactivated. A lot of them can't even open anymore. Okay. So that's what the individual like currents look like. And it's like a, it's like a gradient. So the higher you pre-pulse, the more channels will be inactivated during that pre-pulse, and the fewer channels can open during the actual pulse. And so this is what it would look like graphed. So this part is not what you would graph. You would graph it on something like this. And so a couple things about these graphs that are kind of like not put because they're standard, they're hidden. The first thing is that this reads voltage. It's the pre-pulse voltage, is the voltage during the pre-pulse. You always keep the pulse the same. So it's only the pre-pulse voltage that varies. The other thing is that the I here is the is not the current during the pre-pulse, it's the current during the actual pulse over here. That's what we're measuring. That's what we showed here, like that. Okay. The other thing is that current is often normalized. So we would do all these experiments like this, and like we would figure out whatever the max current was and divide everything else by that. So this is the normalized voltage. And so that's why here, when you pre-pulse at -90, remember you pre-pulse at -90, almost nothing is inactivated. And so all the channels are available to open during the pulse. And so that's why the current is very high. It's like 100%. It's at max basically of what you can get when you pre-pulse at a very low voltage. Contrast that, and then if you pre-pulse at a higher voltage, like -60, you've got some of the channels opening, some of the channels inactivating, but still a bunch are available to open. They're not inactivated, they can open, and so you still get some current. -30 or 40, maybe more inactivated. So the ones that are left at +20 that can open is not so many. And then this isn't even shown on the graph because in this particular experiment, they didn't think it was worth it. But if they did pre-pulse at zero, they would find that almost everything would be inactivated. And so when you pulsed at +20, the current would be very low indeed. And so that would be kind of off the charts over here. And so this is why the results you get are kind of this shape. It's because at low voltages, at low pre-pulse voltages, very little is inactivated. So by that, when you pulse, a lot of current can go through. And then if you pre-pulse at a high voltage, most of them do get inactivated. And so when you pulse, you don't get very much current at all because all of them are inactivated. Okay, so here is a real life example. These folks were trying to study the toxin APA. It's a toxin from sea anemones, and they release it to signal to each other and also to deter predators. Remember, a sea anemone is just like sitting on the ocean floor. It can't really move. It doesn't have any teeth or anything. So it's going to make toxins to try to convince predators that they shouldn't eat it. So before this experiment, people knew that APA bound to voltage-gated channels and affected their behavior. And so one of the things they did was do this pre-pulse protocol, and they were measuring the voltage dependence of inactivation in this graph right here. And you see some of the signals mean like the no toxin, that's the solid symbols. The other ones mean with the channels with the toxin. So what do you think? Based on this graph, how is APA affecting inactivation? Okay, one thing, it doesn't seem to be having a huge effect, but if you look, it seems to be having a mixed effect. So at these low voltages, like at -90, there is less current with the toxin than without the toxin, than normal. What does that mean? If there's less current, that means more of the channels would have been inactivated. And so it means that at low voltages, it seems to be more inactivation than normal. But what about these high voltages? At high voltages, it seems we have the opposite thing. At high voltages, there's more current with the toxin than without it. And so if there's more current, that means that fewer channels are inactivated, right? Because like inactivated channels don't pass current. So at high voltages, there's more current than typical. That's fewer channels inactivated. So there's this mixed effect. Okay. Um, so going back to this diagram here, what have we done so far? So in previous videos, we've talked about how to measure what's going on from going to the resting state to the open state. So you would do measure conductance and current after applying potential gating stimuli. So for a voltage gated channel, that would be our IV and GV curves. That's previous videos. So in this video, what we've added is how to investigate how a channel goes or what a channel is doing, going from the open to the inactivated state. So one thing is measuring current long after the stimulus is given, and the other is using this pre-pulse protocol, specifically to find the voltage dependence of inactivation. Okay, you might notice that we're missing this, a box for this step here, going from inactivated to rest. That's our next video.